Hello, this is Dr. Hassan Abdullah with the course Complexity and Analysis of Algorithms. So, the topic which we are covering in this video is greedy algorithms, and the subtopic is the applications of the greedy algorithm. So, the topic number is 6 in the course outline, and since this is the second lecture, so it's 6B. So, this video and this course uses the supplemental material available at ezmcq.com/goget. This is basically a learning management system, but it's a personalized learning management system. Personalized in the sense that you can set the level of difficulty and the type of questions you would like to practice and you would like to see. And of course, you can also personalize your user interface as per your liking or as per your requirement in terms of color, fonts, size, etc. And of course, you can have a personalized experience of testing yourself, what you have gathered, what you have learned, and so on. So, how to use these features? There are 6 videos which show these features, and these videos are available along with the course videos on my YouTube channel. So, if you type my name, Dr. Hassan Abdullah, on YouTube, you will see these 6 videos and the course videos also. So, now we move on to the supplemental website. And before we do that, let's take a look at the course topics. So, this course consists of 11 topics, and the contents of these topics are the latest one. They are state of the art, and I will be also covering right now we are covering greedy algorithms, and I will be covering advanced algorithms also, which will be randomized algorithms, approximate algorithms, and genetic algorithms. A lot of fun stuff, a lot of useful things, and don't forget to test yourself through the practice quiz. So now we move on to the supplemental website. So we are at the supplemental website, and the questions from 1 to 5 were covered in the video lecture 6A. So now we are at 6B. So we start from the 6th question. So briefly explain the problems solvable using greedy algorithms. So there are not many problems for which greed works as per the published literature and in the textbooks. So we will briefly go over those problems, and we'll discuss and see how the greed works here. And among these 8 problems, we have already covered the Dijkstra's algorithm. We have already covered the minimum spanning tree. Already covered. So in this course, we will cover, or in this video also, we'll cover the job scheduling problem. Okay, to a certain extent, and Huffman coding. Huffman coding, it works perfectly. So let's look at the description. So the greedy algorithms. Okay, there are certain types of optimization problems. For example, find the lowest cost spanning tree, find the coding which compresses the text optimally, and so on. So when making series of locally optimal choices, series of choices, and of course we have discussed why and how it works. So for example, activity selection problem. So given a set of activities with start and end time, select the maximum number of activities that don't overlap. So we have covered this briefly in the previous video 6A also. So the greedy approach is always select the activity that finishes the earliest, okay, and then choose the next one that starts after. So this is perfect. This is all greed. Finishes the earliest. No looking what would happen in the future, and no looking back what had happened in the past. So why the greed works here? Because the problem has the optimal substructure property, okay, and therefore when you choose the earliest finishing activity, okay, then of course it works for the subsequent activities also. So that we have covered in detail in the previous video. All right. So Huffman coding we will cover in detail in this video. So what is Huffman coding basically? We have a set of characters in say English language, and their frequencies. Frequencies mean that how many times they occur in a sentence or in a paragraph or in a book or paper, whatever. And the smart thing is that assign variable length codes. So the words which don't get the same length of code, okay, and what happens that because of this the total length of the encoded message is minimized. So greedy approach is build a binary tree, okay. I'll show you where each leaf node represents a character. So all the way from the root to the leaf, it represents a character, and in between the edges they define the code for the character. And how it works: repeatedly merge the two least frequent characters, so greed is here, least frequent characters, and create a new node, and just keep on doing this, okay. So why grid works? Because most common characters are given shorter codes. So it works because it has those properties which make the grid work. Fractional knapsack problem. So knapsack, I believe everybody knows. So it's a bag we need to put stuff in it. But the knapsack can of course have a limited weight capacity. Okay, and we have different items. Okay, and their different quantity and their different weights. Okay, so the idea is to maximize the weight and maximize the total value of the items put in the knapsack. Okay, and the total value, okay, of ranking taking fractions of, and of course part of item can be taken, but the knapsack can carry a limited weight. I'll explain it in a lot of details. So how do you select the items based on from their value to weight ratio? So here's the, and where's the grid? Highest value to weight ratio. So for example, if the item is, say for example, is expensive, okay, so you would like to place more of that item, but usually the items which are expensive, they are less available. That's the scenario. So why grid works? Why? Because the fractional nature of the problem. Okay, so grid works, right? And then is the coin change problem. But the coin change problem is not applicable everywhere, because it depends upon how the denominations of the coin. So given a set of coin denomination and total amount, find the minimum number of coins. Minimum number of coins needed to make up that amount. Okay, always take the largest coin denomination that doesn't exceed the remaining amount. So in many coin systems, including the US coin system, the greedy approach produces the optimal solution, because the larger coins tend to be more efficient in terms of reducing the remaining amount. So you have the larger coin, and of course that covers the smaller coins also. So again, right? So larger coins, that is greed. So the greed works here. Job scheduling problem with deadlines and profits. Given a set of jobs with deadlines and profits, schedule the jobs to maximize the total profit. So we are basically trying to maximize the total profit, right? And each job can only be scheduled once and must finish by its deadline. So sort jobs by profit, because in descending order, and schedule them as late as possible with their deadline. So as late as possible, greed. Sort by profit, again greed. By scheduling high profit jobs as late as possible, you maximize the profit. Okay. So this is just to give you an idea that there are not many, but there are some problems. So minimum spanning tree we have already covered. Dijkstra already covered. Optimal merge pattern. So what is optimal merge pattern? Given a set of file sizes, okay, repeatedly merge the smallest files to minimize the total cost of merging, right? So always merge the two smallest files first, and then you keep on repeating it. So the minimum total cost. Okay, fine. So why the grid worked for these problems which we have considered? Because they had the optimal substructure property and the greedy choice property. So what is the, I'm just repeating here, what is the optimal substructure property? Combining optimal solutions to the subproblems. Okay, and greedy choice property, choosing the best local option at each step. So because these two things work, therefore grid works. And of course, always remember that greedy algorithms don't work for all problems. As a matter of fact, it does not work for the 0 1 knapsack problem. 0 1 knapsack problem is that you take the item completely. So you take this item completely, you take this item completely. Fractional knapsack is you take part of the item. All right, so we move on to the next one. So what is Huffman greedy coding algorithm? So the Huffman greedy coding algorithm works because of the greedy choice property, making the locally best choice, and optimal substructure property. What is the optimal structure property? It is combining optimal solutions, local optimal solutions, results in the global optimality. All right. So how does it works? It works by first you have to make the greedy choice. These they already covered. So how does the Huffman coding works? Create a priority queue or min heap. In this case, min heap. Okay, and each character is treated as a node with a certain frequency of its occurrence within a sentence or a paragraph or a chapter. And these nodes are placed in a priority queue. Okay. When we say character, it means the English language characters. Okay. So we based upon their occurrence, we make a min heap, right? And the priority queue ensures that nodes with the smallest frequencies are easily accessible. All right, so that's the purpose. Build the Huffman tree. How the tree is built? Repeatedly extract the two nodes with the smallest frequency. So you first of all you take the root, and then you settle and heapify, and then you pick the next root, and then what you do is you extract, create a new node whose frequency is the sum of the two nodes, right, which were extracted, and this new node becomes the parent of the two nodes, and this goes back into the priority queue, and this process is repeated till only one node remains in the queue. This node is the root of the Huffman tree. Okay. So once the Huffman tree, so assign binary codes. Once the Huffman tree is constructed, assign binary codes to the characters. Starting from the root, assign 0 for the left branch and 1 to the right branch. So this is basically is not the absence or the presence of an edge, right? So the binary codes to the characters starting from the root, assign 0 for the left branch, right, and 1 to the right branches. All right. So the path from the root to the leaf gives the Huffman code, which is a binary code, and then generate the final code book, the characters and the corresponding. So the path, the coding of the path of the leaf to the root is the code for that character. All right. So if you're interested to read more about it, here are the reading material. So let's do Huffman coding. All right. And let's look at all the. So these are the English language characters. We are considering 5 characters, and this is their frequency of, or frequency of. I'll tell you what it is. So it's their weight value. So this is the. So how do we go about variable length codes, right? With two input characters with shorter codes assigned to more frequent characters. This is the smart thing, because the characters which occur more, if their length is less, so the overall length would decrease, and the characters which occur less frequently, they can have the longer length because they are occurring less. So we have this data set, and this is the probability of occurrence of A, B, and so on. And this is, of course, this is not sorted. So first of all, create the nodes characters, and you have it. This is data set. This is the input. Build a main heap or a priority queue. Okay, and we create the main heap, and this is the order in which they are going to be extracted from the root of the main heap. So extract the two nodes with the lowest frequencies, 0.1 and 0.15, combine them together, and the result is 0.25. Okay, 0.1 into 0.15, 0.25, and this is the new node of the Huffman tree. So see, A and B are combined, so we have A plus B. Let me highlight this. So A and B are combined, right, and A plus B is the new node, and the overall frequency or the weight of that node is 0.25, which is 0.1 plus 0.15. Repeat this process. Okay, so next we see that which is the smallest ones. Okay, and which is for D is 0.16, and 0.16 is smaller than 0.29, and 0.16 is smaller than 0.3. So we combine the smallest ones, or in the Huffman coding, the smallest one is combined. So when we combine this, so we have D plus A plus B, and the overall frequency is 0.41. So we have this, right? And we keep on repeating this process till what happens, that till we reach and we have a single node. Okay, we have a single node, right? And we have the single node. Let me highlight it. Okay. So now how the traverse left assigning a 0, and traverse right is a 1. Okay. So I will also show you the tree also. So this is how the codes are assigned, right? And this is the Huffman code. So if I will zoom this, right? So you see that this is the input, okay? And then we did a combination, and before that combining, we sorted them. This is the sorted, and then we combined 0.1 into 0.15, we have 0.25, okay? And then the next smallest one is combined, which was D, because E is 0.29 and C is zero point 0.3. So this is the new weight, 0.25 plus 0.16 is 0.41. And we keep on doing this, right? Until we reach the end. And the root has a value of 1. Root has a value of 1. So left are zeros and right are 1. So the code for, so this edge is 0, 0, 0, right? And B is 0, 0, 0, 1. So let's look at the codes. So the code for A is 0, 0, 0, and the code for B is 0, 0, 1, and so on. So this is how Huffman code works. Okay, now we look at a different problem. Now consider jobs with running times of 3, 5, 6. This is and so on. You can see the minutes. and we have three processors. Now the problem is, now we would like to assign or schedule the jobs in such a way on three processors such that the overall time to completion is reduced. That is the requirement. Now let's look at the working of this scenario. So what we have the jobs, and we sort the jobs by their duration, okay, in descending order. Of course, we can do it in ascending order also. Then we initialize the processors. Initially, they don't have any jobs assigned to them, and then we assign the jobs based upon their completion time. Okay, so we are assigning based upon the completion time. So the grid is here. Okay, so longest completion time, then the next one, and the next one, and so on. So the grid is here, and then we get the final solution, and we review that solution and try to figure out that how good or bad that solution is. So let's go into the details. So we have these 9 jobs, okay, and these are the completion times, and we have sort the jobs in decreasing order of running time. Okay, so sort the jobs by in descending order. Okay, so we sort them in descending order. So initially there are no jobs assigned to the processors, so the processors are free and no jobs are assigned to them. And then we assign the job which the longest completion time, which is job number 9, to processor 1. It requires 20 minutes to completion. Okay, and while this processor is busy, then we assign the next job with completion time with 18 minutes. So job 8 is assigned to processor number 2. All right. And then we assign the third job, which is job number 7. Completion time is 15 minutes. So this is how the assignments have taken place. Right. So what happens after 15 minutes, that processor number 3 is becomes available. Okay, and it becomes available, and now it busy until 29 minutes. Why? Because first of all, it consumes its own 15 minutes, and then it got the next shortest job. Okay, and its duration was how much? 14 minutes. So 15 plus 14 is 29 minutes. Okay, so then what happens that after 18 minutes, processor 2 becomes available, and the next shortest job, okay, is assigned to it. So it becomes busy for the next 18 plus 11, 29 minutes. And what happens after 20 minutes? After 20 minutes, processor 1 becomes available because 20 minutes have passed, and the next job is assigned to it. The duration of that job is 10 minutes, so the total it becomes busy for 30 minutes. Okay, now see, all right. So this keeps on going, and we keep on assigning the jobs as and when the processors become available, right? And in the end, what we have that processor one got busy for 33 minutes, and you can read it. What would the total time taken? Because we are doing in parallel processing, so until processor number 2 is available, okay, is does not finishes, nothing can finish. So the time taken is 35 minutes. So this is how it looks if we draw it on a scale, and we can see that processor 1 took how much time, and the longest time taken was processor 2 was busy for the longest time. So the total time taken is 35 minutes. Now the question is this optimal? Okay, can we do better than this? So let's look at another strategy now. Okay, the times remain the same, but now the shortest job is going to be assigned. Previously we assigned the longest job, so when we assign the shortest job, then the total time, that the maximum time taken is by processor number 3, which is 40 minutes. So this is not it's not good. Okay, so the greedy algorithm itself is fast, but this scheduling strategy was not good. Okay, so we are down from how much, from 35 minutes to, we have basically it has deteriorated to 40 minutes, and obviously this is not a better solution. So if you look at this example, if you look at this example, can we figure out that what would be the property of the optimal solution? That will look at the last question of this series of lectures. Okay, so now what has happened, that we have completed the 5 questions. So with this we end this part of the lecture. Thank you.